matrix transformations then. So what's the point of matrices? Well, that's because they can do stuff like this. Right, let's start with if a point, just any old point P, which has coordinates x, y, is transformed to a different point, so P dash, we say its coordinates are x dash, y dash. Then P is said to have been mapped to the image P. Right, so the mapping is where it's moving, and the image is actually where it ends up. So, for example, when the point 4, 2 is transformed by a reflection in the y-axis, obviously the x values in that case will switch, like polarity, I suppose. They become negative or positive. They change. So, in this particular case, 4, 2 is mapped to negative 4, 2 because it's reflecting the y-axis, yeah? And let's say we've got this point here, 3, negative 1, so 3 to the right, 1 down, is transformed by rotating through 270 degrees. If we rotate that, it ends up at this point, right? Negative 1, negative 3. Just take my word for it, it does. That case, this point here, 3, negative 1, is mapped to negative 1, negative 3. These end ones are the image of each point. Fair enough? Right, we always assume, by the way, that a rotation is anti-clockwise in this course, unless we are told otherwise. It's always going that way, all right? Unless you're American, and then learn the word anti-clockwise. Right, okay, onwards. A transformation can be defined by a matrix, funny enough. Otherwise, this short video would be really pointless. And it is a short one, this one. Right, for a transformation that maps 1, 0 to AC, this is the transformation matrix. You would have AC here. Now, these points will become relevant in a future video, right? But for now, they're just any old point. And then 0, 1, which maps to BD, would be like this, BD over the other side. Right, when a matrix acts on a point, we use the point's position vector from the origin. So essentially, because it's coming from the origin, that's going to be a coordinate. So the position vector of negative 1, 5 is obviously 1 to the left and 5 up. So it looks like this. Note that this looks just like a normal vector, right? But it has square brackets. Obviously no fraction lines or anything, because it's not a fraction. It's a position vector. And we just write it as a 2x1 matrix. So in general, for a transformation matrix, let's try that again. For a transformation matrix, ACBD, acting on a point xy, the image x dash y dash is given by this. It's acting on xy, and it gives you the position vector of, the new image of x dash y dash. Yeah, so that we'd obviously expect to see numbers in there. All right. Okay, let's leave that parked at the top there, so you've got the basic idea. So work out the image point of negative 2, 5. Let's get a decent colour on this. For the transformation matrix 2, negative 2, etc. So we have 2, negative 2, 3, and 1. And we want that to act on our point, which is negative 2, 5. So just like the last video, I'm going to imagine taking these numbers and plonking them on top here. So negative 2 times positive 2 is negative 4, and 5 3s are 15. So 15 take away 4 is 11. And negative 2 times negative 2 is positive 4. 5 times 1 is 5. Put those together, and we get 9. So the image point will be 11, 9. Yeah. Happy with that? Good. Right, what about the transformation matrix 1, 0, 0, 1? Work out the image of each of these following points. Right, and I'm going to do some working out above, I think, on this one. Just so I've got a bit of space. So 1, 0, 0, 1. Now, anyone that's worked with matrices will know instantly what that matrix is, but we'll come to that in a minute. So what happens? Well, we've got 3 times 1 is 3, and 2 times 0 is 0, so that's just 3. And if we multiply the bottom row, we end up with 2. Basically, the image for this one is 3, 2. Let's try it again. So 1, 0, 0, 1 times by the next point, so negative 1. That's supposed to be a 1. And positive 5. Well, negative 1 times 1 is negative 1. 5 times 0 is nothing. So that is negative 1. And negative 1 times 0 is 0. 5 times 1 is 5. Again, that one hasn't changed. And in fact, I'm not going to bore you with it. If we do it with all of these, they actually don't change at all, which is curious. We'll come back to that. How would I describe the transformation? Well, there isn't one. It doesn't move. It doesn't go anywhere. Let's try it with something that might be more interesting. Change colour again. And again, I'm going to use a bit of space somewhere else on the page. I'm going to put it up here. So 1, 0, and then 0, negative 1. And we're going to times that by the position matrix of the first one. Let's rewrite that. That should be a 2. And that's a 1. Should we just be a little bit neater? Seeing as I can rub that out. Okay, so this should be 2, 1. 2 times 1 is 2. 1 times 0 is nothing. So that stays as 2. But the bottom one, 2 times 0 is 0. 1 times negative 1 is negative 1. So the image here is 2, negative 1. Okay, let's try that again. Oh, we could cheat here a little bit, couldn't we, actually? We could just rub out these numbers, put new numbers in. Let's try it again with the next one, which is negative 4, 3. So negative 4 times 1 is negative 4. 3 times 0 is nothing. So that number stays the same. But the bottom number, when I multiply it, will be negative 3. So negative 4, negative 3. And in fact, if I keep going along, each time, the second number just changes what I sort of call polarity. You know, it changes from being negative to positive or positive to negative. So what does that mean? If we think about a very basic little set of axes, what's happening to our points? Well, the second number is the y one. So each, if it's a negative point, it goes up to being positive, and if it's a positive one, it goes up to being negative. It's basically flipping along this line. This is a reflection in the x-axis. All right, if you can read that. It's basically flipping along the x-axis up and down. So reflection in the x-axis. Interesting. Let's go back to that matrix though. This matrix, the 1, 0 and 0, 1, is called the identity matrix, and it's signaled as being I, or capital I. And the identity matrix is important because when you multiply any matrix by the identity one, you can do it either way round, either AI or IA from matrix A, and it will still equal the original matrix. And you might think, well, what's the point? But there is point to that. I'm just not going to tell you right now, all right? But the identity matrix is the matrix which performs no transformation upon something. All right? Okay, it's used, no movement occurs at all. Right, as I say, this was a short one, so go off and do some questions about just doing basic transformation matrices. If you're working with this book, the Hodder Education one, which is where all this sort of stuff comes from, which I'm using, not sponsored by them though, but it is a great book, so go buy it. Even if you're not doing it, why not go buy it? Anyway, yeah, I'm boring you. I know, I'm boring me. It's time to make a coffee, and then I'll come back for another video. So, see you again. Bye-bye.